Dear, dear ladies and gentlemen, dear honorable guests, dear colleagues and friends, it's a great honor and pleasure for me to welcome you on behalf of the National Academy of Sciences of Ukraine. Today we have a very interesting and very important event. Not only scientists gathered here, but also students, teachers, and alumnus of the Kiev Natural Science Lyceum number 145. And I am very pleased to see the young faces of those who I hope will soon join the Ukrainian scientific community. I have every reason to hope for this, because hundreds, maybe even thousands of graduates of the Kiev Lyceum of Natural Sciences work in the institutes of the National Academy of Sciences of Ukraine. Among them are prominent Ukrainian scientists, members of the Academy, professors and doctors of sciences. And taking this opportunity, I would like to thank the leadership and teaching staff of the Lyceum for the great work they have been doing for many decades. I am glad to welcome our Swedish colleagues who are outstanding Swedish scientists and who expressed desire to come to us in this challenging time and give interesting lectures. We consider their visit as an expression of their support and solidarity to the Ukrainian scientists, to the Academy of Sciences of Ukraine. And we're deeply grateful for such support and solidarity. In our globalized society, international cooperation facilitates opportunity for research and self-improvement. We know that every fifth scientific article in world is written in collaboration with researchers from various countries. Thanks to enhanced communication methods and simplified international travel, it's now easier than ever for scientific collaboration and researchers to work with their counterparts abroad, greatly facilitating the exchange of academic knowledge and ideas. The opportunity to share experience is crucial for academic and scientific achievements. Constructive discussion of ideas plays a central role in their development, and international collaboration contributes significantly to this progress. Communication and personal connection, both at the academic and administrative levels, are optional means of building a relationship through meetings, exchanges, and academic events. We are very glad to welcome here Professor Mats Larsson, who is a professor of Stockholm University. He is a full member of the Royal Swedish Academy of Sciences. He is a foreign member of the National Academy of Sciences of Ukraine. He is a member of the Nobel Committee for Physics, and he is a winner of the Vernadsky Gold Medal, the highest award of the National Academy of Sciences of Ukraine. Professor Larsson is so kind to give the lecture, Nobel Prize, the oldest and most prestigious scientific award. Professor Larsson, the floor is here. You're very welcome. Let us welcome.
Thank you. And I hear now that the sound system seems to work. And I would like to start with video greetings from that was recorded only 5 days ago in Vienna. And what you see here is a foreign member of the Ukrainian Academy of Sciences and Nobel laureate of last year, 2022, Professor Anton Zeilinger. And I will now hope that it will work to his greetings.
It's a very interesting number. And the Ukrainian Academy of Sciences, I hope that very soon that's the situation again, that we can meet in person and talk science and
So,
the importance of for the future.
I realized it was a little bit difficult to hear, but it was not possible to hear. I wonder how can we, yes, can we?
Okay, I'm happy to talk to you via my very first presentation to school 45. Very interesting number. The Ukrainian Academy of Sciences. I hope that very soon we will have a situation again where we can meet in person and talk science and actually the importance of personal international relations. Thank you.
Yes, I realized that the sound quality was not. Okay, okay. Yeah.
Мне разрешили перевести, что Антон сказал. Это действительно было 5 дней назад. И, в общем-то, в том году на Нобелевском награждении мы уже знали, что Матс должен был приехать в академию и выступить перед учениками 145-й школы. Вот. И он хотел поехать, но буквально месяц назад сказал, что его семья не получилось, и он послал такое к вам приветствие. В этом приветствии он сказал: я приветствую всю Академию наук и учеников 145-й школы. И он сказал: 145 – очень интересная цифра. Я так думаю, наверное, потому что очень большая цифра. В Европе, видно, не привыкли к школам такого большого, там 205, да, 145. Вот. И он высказал, он пожелал всего наилучшего, и он сказал, что самое главное, что он надеется, что в будущем он обязательно посетит Киев и выступит персонально, как бы для вас. То есть, такое маленькое послание, очень приятно.
Okay, and then I will now turn to I will give two lectures, two short lectures. One will be about how to get the Nobel Prize, and the second one will be this year's Nobel Prize. This is Alfred Nobel. He was born in Stockholm, Sweden, but his family later on moved to the Russian Empire, where he was also active for several years. His most important contribution was that he invented dynamite. He didn't invent the explosive nitroglycerin, but nitroglycerin was very dangerous to handle because it was very fragile and there were many accidents. So what he did, he invented a method where you could absorb nitroglycerin into a soft stone, and this made it much more safe to handle the explosive nitroglycerin. And he filed a patent in 1864, and he made a lot of money on this because dynamite was used in mines to prepare tunnels and so on and so forth. So he made an enormous fortune on this, but he never formed a family. So in 1895, he decided to donate his entire fortune to a prize. And this prize was composed of 5 parts. And I will show you a little bit. This is his handwritten will that he wrote in Paris in November 1895. And what he formed here was, he divided the prize in 5 parts: physics, chemistry, medicine, literature, and peace. And for physics, which is what I'm going to concentrate on now, is that he said that it should be to the person who shall have made the most important discovery or invention within the field of physics. We had a slightly different formulation for chemistry, where he said it should be the most important discovery or improvement. And this seems like a small difference, but it has been actually something that we have always have to think about in physics. It has to be the pioneer we have to award, the person who did it first. Whereas the chemist, they don't have to be as careful. They can also think about who has improved a method that had been very important for chemistry. Not only did he explain what prizes there should be, he also defined the prize awarding institutions. And for physics and chemistry, he decided it should be the Royal Academy of Sciences in Sweden. Whereas the other prizes, he had other selections for medicine, for example, the Karolinska Institute, in literature, another academy, and for the Peace Prize, the Parliament in Norway. So, so the first prize in physics and chemistry and the other areas, the other disciplines, was awarded in 1901. And at that time, there had been all the money that he had been put into a foundation. And this money was then used to award the laureates. And in the first physics prize was awarded to Röntgen, or as you would say, maybe Röntgen, for his discoveries of the Röntgen rays. So this is typically how the year runs through. The Nobel Committee, which is a part of the in the Royal Swedish Academy of Sciences, we have 10 sections, of which one section is physics. In the physics section, we select maybe 5, 6, 7 persons who will form a Nobel Committee, and they will do all the preparatory work to find a proposal for a Nobel laureate a particular year. So the Nobel Committee will send out letters to several thousands of scientists in September, a particular year, and then they ask for nominations, which should be submitted and arriving at the Nobel Committee before February 1st the next year. So in February, we have like maybe 250 to 350 persons that have been nominated. And then we have to look into what special areas where there has been breakthroughs in physics. And what we do then is that we typically send out requests for expert reviews of these areas where the experts not nominated to be laureates, but still on a high level. We ask them to write a review about this area. Is it sufficiently important to consider the Nobel Prize? And if it is sufficiently important, we ask them also to at least propose 3 names of the people that have made the most important contributions. Then we work during the summer. We have all the reports, we have all the nominations. We form a short list, and eventually in August, we go to some place where we stay for a few days. We write a report to the Academy of Sciences, and we have to come up with a proposal for the Nobel Prize for that particular year, which means that we have to select 1, 2, or 3 laureates. Maximum is 3. And then in September, this proposal is discussed in the physics section at 2 different occasions. And then in October, the full academy gets together to make a decision. And once we have made the decision, we go to a special room and make a phone call to the laureates, because we want them to hear it directly from the Nobel Committee that they have been awarded the prize. And once we have made these telephone calls, there is a press conference, and I will show you a picture from this. So nominations is by invitation only. We get, of course, nominations by crazy people, but we throw them away immediately. All the nominations and expert reports and all the documents concerning the Nobel Prize are kept strictly secret for 50 years. And after 50 years, historians of science can look into the archive and if they want to write something about the special prize. We ask always for individual nominations. We don't want to have nomination by a group of people that have been gathering at the coffee table and make proposals. We want to have their individual personal opinion. This is important. And also important is that the person who is not nominated a particular year cannot be considered for a prize. And we cannot award the prize to somebody who has deceased. It must be a person who is still alive. And this can be nervous when we propose a person who is 95 years old. You never know. So as I mentioned, we send out these letters of nomination. We get the submission, consultation with experts, writing report, and discussions in the physics section. And then finally, in early October, we have the decision in the Academy. And this picture you see here is our Academy of Sciences building. So here is a picture from the press conference on October 2nd, 2018. So what you see is to the left, Olga Botner, who was at that year the chairperson of the Nobel Committee. In the middle, you see our permanent secretary, who is always opening the press conference. And to the right, it's me, who will give a 5-minute long presentation of this year's prize in 2018, which was a combination of, you can say, a laser prize. And here I am giving the presentation. This is broadcasted on the internet, and the whole room is filled with journalists from different countries, and afterwards, after my presentation, we usually try to call one of the Nobel laureates so that the journalists can ask a question directly to the Nobel laureate. That was in October. Now we come to December. December 10 is the big day. This the day when Alfred Nobel passed away. And this is when we have the Nobel Prize award ceremony. And I will show you some pictures from this, how it works. First, we have the prize ceremony in the concert house of Stockholm. So here is the concert house. And it's filled with people. I think Professor Kertel has once been participating in this prize ceremony with his wife, Ludmila. And here we have the ceremony from last year. What you see to the left are the Nobel laureates coming in from one side. You see at the back, you see Anton Zeilinger, then John Clauser, and Alain Aspect, the 3 laureates. And in the middle, you see a statue of Alfred Nobel. And to the right, you see 3 members of the committee, Nobel Committee. So I'm sort of escorting Professor Zeilinger. Eva Olsson, my colleague in the committee, she is escorting John Clauser. Ellen Mons, another colleague in the committee, she's escorting Alain Aspect. And the person who will hand out the prize is the Swedish king. So what you see here is the royal family. It's the king to the left, the queen, and then back you see Crown Princess Victoria and her husband. So they are always sitting here on the stage. And in the back, you see members of the Nobel committees for chemistry, physics, and other people that are involved in the Nobel Prize. Then we have the presentation speech. And this year, last year, that is in 2022, I gave the presentation speech. And I like to draw your attention to the Vernadsky Medal. And this ceremony is broadcasted live directly in the national Swedish TV. So a lot of people are watching this. And of course, it's a little bit nervous to go up on stage. And you know that it's broadcasted across all of Sweden. And I think now these days, people also outside of Sweden can think about how they can tap into the Swedish TV. So earlier we gave the presentation speeches in Swedish, but from last year in Oh, yes, sorry. It's the Vernadsky Medal and the Medal of the Ukrainian Academy. Yeah, okay. And here you see now the 3 laureates listening to my presentation speech, and you can see that they look quite serious. This is the highlight of their scientific life, obviously. And even Professor Seilinger, who is usually very humorous and laughing, he's a little bit tense here. And here you can see him being awarded by the Swedish king. And so this is always the tradition. It's the king who is handing out the medal and some other diploma. After the prize ceremony, we go to the Nobel banquet, which takes place in the City Hall of Stockholm. This is usually very difficult to get tickets here. Many people are very interested to come to this banquet, but so it's a lot of work for the Nobel Foundation, who's organizing and hosting this dinner to select what people should come or should not come. The Nobel committees are always invited with their spouses. And here you can see a picture from the banquet. It's a very big banquet with maybe 1,000 participants. And you see in the middle the honorary table with the Nobel laureates and the king, the royal family. Maybe the Swedish prime minister will also be at this table. And then you can see perpendicular, there are several tables where the other participants of the dinner are sitting. And this banquet is broadcasted live in Swedish national television. So one can sit at home and watch how we are having a long dinner with some entertainment. Usually you sit here for between 3 and 4 hours, so it's a very long event. And after the dinner, we took a photo. Here you see Victoria and me at the dinner, and if you want, one can then also go up and dance and entertain. And I think now I'm coming to the end. And here's a photo from last week with, once again, Professor Seilinger, with 2 of my colleagues in the physics section of the academy. And we had, and this was a visit our physics section had at the Austrian Academy of Sciences. And after discussions with the Austrians, we realized that our academy is quite different from the Austrian Academy of Sciences, but it's much more similar to the Ukrainian Academy of Sciences. So there are definitely similarities with your academy operating a number of research institutes, which we don't have in Sweden. It's more like a learned society. This was my last picture from the Nobel, and now I will turn into the next presentation. So what I decided to do was to take my presentation this year at the press conference and just expand it a little bit so that you can get some flavor of how this press conference works. So this year's Nobel Prize was awarded to Pierre Agostini, who is presently at the Ohio State University, Ferenc Krauss, who is at the Max Planck Institute of Quantum Optics in Garching, Germany, and a Swedish colleague actually this year, Anne Lullier, who is active at Lund University. And this was the first Nobel Prize ever awarded to somebody active at Lund University, which is the university in the most southern part of Sweden. And they were awarded a prize for experimental methods that generate attosecond pulses of light for study of electron dynamics in matter. So I started my presentation then by saying that this year's Nobel Prize in Physics is about the time scale of attoseconds. And what is this time scale? Well, an attosecond is related to a second. A second is typically the heartbeat of a human. I mean, if you have 60 beats per minute, you have 1 per second. And if you calculate the age of the universe in seconds, you have the same relation between the age of the universe and 1 second as the relation between 1 second and an attosecond, 10 to the 18. So this gives you a feeling for how short time scale 1 attosecond is. And what I plotted here is the pulse length of a laser, the shortest pulses that could be produced by lasers during different years. And you see that it decreased quite rapidly down to about 1980. Then there was a long plateau when nothing changed until the beginning of 2000. And the question is, why? Was it not possible to make shorter pulses than about a little bit less than 10 femtoseconds, say 5, 6 femtoseconds? Well, this is because there is a fundamental barrier to make shorter pulses. What is this fundamental barrier? It's the following. In order to have light, you must have at least one single cycle of the electric field of the laser. And if you are in the optical region, the shortest pulse you can make in the optical region is somewhere between 1 and 2 femtoseconds. And this was called the femtosecond barrier. And nobody knew how to penetrate this barrier. Until 1980, all the advances had been in technology. Laser technology had made it possible to go to shorter pulses. But around 1980, that was no longer possible. Some fundamental physics had to be invented in order to pass this barrier. This is my colleague, Anne Lullier. I've known her for many years. She's from France originally, but she moved to Sweden and got married to a Swedish colleague of mine in around 1995. She was active in France, in Paris-Saclay, and in 1988, she and her colleague made an experiment where they took a gas jet and focused a strong laser into this gas jet, and they were interested in, they asked the question, can we see some fluorescence? Can we see some light from this interaction between a strong laser and a gas jet of inert gases like xenon or neon or argon? But they also looked for photons in the forward direction, in the same direction as the laser is shining. And of course, they had to use a grating to filter out the laser light. They didn't know what to expect. They had a detector, as you can see here. A photon detector, but they didn't really know what to expect. Here's a historic photograph that I just recently got from Lund. This is the original setup. I will not go through it. This is just for historical reasons I show it. It's a rather, as you can see, it's rather small and simple setup. So to their surprise, what they found was that they found so-called overtones of the basic frequency of the laser. The laser was about 1 micron. And then they found photons, overtones of these 1 micron photons. So what you see on the y-axis is the intensity, and on the x-axis you see the wavelength of these photons. And what they saw was that the first overtones rapidly decreased in intensity. Then they saw a long plateau, and finally a cutoff where the intensity died off. And initially they could not understand how to explain this unexpected feature of the overtones. But slowly emerged a picture that could explain why you see these overtones. And what you see here is, to the left, you see an atom, which is now starting to interact with a strong laser. The strong laser will deform the potential. You see the nuclei forms a potential for the electron. Normally, the electron would stick to the atom, of course. If you don't do anything, it's a stable atom. But with the strong laser field, you deform the potential, and the electron has a chance to tunnel out and become a free electron. But it's not entirely free because it's still, the laser is still on. And at one point, the electric field of the laser will change direction and force the electron back to the atom. And then the atom captures the electron, which has now quite a high kinetic energy. It must get rid of this kinetic energy. As you know, energy is always conserved. And it does it by emitting photons. Photons at short wavelengths. And depending on how far the electron went before it came back, you will get different wavelengths. And this is exactly this plateau that I showed you. And if you sum up photons of different wavelengths, you get interferences. And the more different wavelengths you have, the more interferences you can get and the shorter pulses you will have. This was realized then that this is the way to break the femtosecond barrier. This is how you can make attosecond pulses. What I showed you was the example of one atom. But in the gas jet, you have many atoms. So the question, the critical question for the scientists and Aurellia and her colleagues was, is it possible to get these many atoms to work in a synchronized way? And at the press conference, I gave this as an example. If you have a symphony orchestra, if every member of the symphony orchestra plays whatever he or she wants, there will be no music. It will just be noise, just disturbing noise. So you have to have all the musicians playing in harmony. And it's, of course, the way you do it is with the conductor. And it turned out that it's the same for atoms. It is possible to design the experiments so that you get a phase matching between the atoms. And this was the critical key to obtain attosecond pulses. So there were sort of two steps, the plateau, and then getting all the atoms to be phase matched. And here is an example of an experiment that was done, an experimental setup. You take a laser light, say 1 micron or 800 nanometers. You split it up in two directions. One direction goes, the laser light is not changed, but it goes into a delay stage. But you can change the time difference between the pulse going to the left and the pulse going straight on. The pulse going to the left will then go into a gas jet, just as I showed you earlier, produce very short pulses. And then eventually you overlap the original laser with these short pulses, the attosecond pulses, and you combine them, you send them into an experiment, and you have an observer who will detect the electrons from the experiment. So the breakthrough in producing attosecond pulses, and this is what we awarded the two other persons for. The first one experiment was done in Paris, Saclay, by Pierre Agostini. He produced a pulse train of 250 attosecond pulses, and he called his technique rabbit. In this field, they like to have these animal names, reconstruction of attosecond beating by interference of two photons. So the idea here was that you take the attosecond pulses, you overlap them with infrared probe pulses, you get interferences, you have an atom ionization, and you get a signal out. This is a red signal you see. This is an electronic wave packet, which is a replica of the attosecond pulses. So you can actually see how the attosecond pulses look like. And this was, of course, a critical thing. How do you detect, how do you know that you have attosecond pulses? In Vienna, and I actually visited Vienna last week, as I mentioned, I Anton Zeilinger. So I saw the laboratory where Ferenc Krauss had been active, and he produced something called isolated attosecond pulses with a slightly different technique than Pierre Agostini. And his experiment gave 650 attosecond pulses. These two methods are still, 20 years later, the existing platforms for doing attosecond physics. Of course, everything has been improved. You can make much shorter pulses now. You can make 50 attosecond pulses. People have developed very clever techniques for experiments. But basically, these two platforms are still the existing. And here you see a little bit more of a technical design of how the experiment works. Eventually, you overlap the two pulses, the infrared laser pulses and the attosecond pulses, the blue, with the target, and you detect the electrons with the so-called magnetic bottle spectrometer. So finally, I come to applications. There is a new field now being developed called attosecond chemistry. Earlier, we had femtosecond chemistry, where one could monitor how the atoms are moving in a molecule with so-called pump-probe experiments. What you can do now is to see how the electrons are affecting the movement of the atoms. So it's really the electrons that are deciding what's happening. These are the active workers in the molecule. Charge migration in molecules, coherent attosecond processes. You can in a bigger molecule, you can initiate something, and then you can see how rapidly the charge in the molecule is spreading, and this is also on a very short time scale. Electron ionization timescales, typically in the attosecond regime. Ultra-fast metal insulator transitions. You can switch how a dielectric can go from being a conductor to being an insulator on an attosecond timescale. And finally, which is a direction that Ferenc Krauss has taken, is to use molecular fingerprinting applied to biological samples like blood plasma. The idea here is that you should be able to detect many molecules. I mean, in a blood plasma, you have thousands of molecules. And he's now looking into the possibility of not detecting all the molecules, but detecting subtle changes in the fingerprint. And if you can do this, the idea is that you should be able to detect diseases at a very early stage. Let's say, for example, lung cancer. This is a very deadly cancer type. And if it's possible to detect lung cancer at a very early stage, of course, you can then start a treatment earlier than what's possible now. So this will be very interesting when the laureates are coming to Stockholm in December. They will give Nobel lectures, and I will, of course, attend these lectures. And just to give you an impression of the timescales here, as I mentioned, electron ionization. Let's take a simple molecule like neon. 10 electrons, and what people now have been able to measure, Enlillier, for example, is the following. Let's say, take a neon atom and pose the following question. If you ionize a 2s electron or a 2p electron, will they be ionized on the same time scale? No. It has turned out that the 2s electron leaves the neon atom 21 attoseconds faster than the 2p electron. This is just, shall we say, a first step to understand ionization. And more recently, there has been more advanced experiment addressing the question, let's ionize water. If you ionize water in the liquid phase and in the gas phase, will the electron leave at the same time scale? And the answer is no. You measure electrons coming from water in the liquid phase that you enter through a nozzle, but there will also be gas phase water molecules surrounding this liquid phase, and you can measure the time difference. It turns out that the electrons coming from liquid water is a little bit slower, about 50 attoseconds slower than electrons coming from gas phase water. And this is just the beginning of a type of experiments that I'm sure we will see a lot more in the future. So I'm coming to the end, and I once again acknowledge our 3 laureates this year, Pierre Agostini, Ferenc Krauss, and Anne Lillier. So I thank you for the attention.
Thank you very much, Professor Lance, for very exciting presentations. Dear colleagues, does somebody like to put questions? You're welcome.
Oh, dear Professor, what is the physical explanation of this difference between liquid water and gas water in time delay?
Yes, that's a very good question. It turns out that the electron in the water in the liquid phase is slowed down a little bit by these the different shells. I mean, if you take a single molecule in water liquid, there will be other water molecules surrounding this water molecule, forming shells, and it's these shells surrounding a water molecule that is ionized. That's what's slowing down, and this means that you can for the first time, I mean, there has been, of course, over the years, many experiments on liquid water. But in these experiments, the electrons are basically frozen. I mean, you cannot see the electrons. When you do the attosecond experiments, the water molecules are basically frozen. I mean, the time scale is so short, so they don't have time to move anything. So you have these shells, and that's what's slowing down the electron in the liquid phase.
More questions?
Is it the same explanation about P and S electrons without water?
The same as?
About velocity of outcoming electrons, P and S states.
Oh, P and S. The P and that can be explained by, I mean, you have electron correlations. So theoretical calculations can understand this difference between 2s and 2p's. These are very complicated calculations, many electron calculations. You cannot use a single electron picture. You have to take into account many electrons. And it turns out from these calculations that 2p is a little bit slower than 2s. I don't think it's possible to make a very hand-waving argument for this. I mean, you really have to look into the details of the calculation, many body perturbation calculations.
I have a second question. Maybe it has no answer, but it is interesting. Can somebody explain why, for example, such outstanding person as Bogolyubov has no Nobel Prize?
Yes, I can actually explain that, because he was considered, as I mentioned to you, there is the 50-year secrecy of the archive. But the prize in superconductivity was awarded in 1972. So this means that now in 2023, I'm allowed to talk about the prize to superconductivity in 1972. And you're quite right. I mean, there was absolutely nominations and consideration of Bogolyubov. There were even different opinions in the physics section. There was a few people more in mathematical physics that favored Bogolyubov as being one of the laureates. Of course, there was also the Bardeen-Cooper-Schrieffer, which eventually got the prize. So the critical question in 1972 was, should one break up the BCS trio to include Bogolyubov, or should one keep the BCS together? And at the end of the day, it was considered to be keep BCS together. So that's the explanation.
Dear colleagues, more questions?
Professor Larsson, how do you think the attosecond spectroscopy may give us the answer why difference between liquid water and gas water? No, for example, on the dielectric constant for liquid water that is 81, but for the vapor water that is close to 0. Yeah. Can we have answer?
I don't think that the attosecond experiment will give you the full answer. I mean, as you know, I mean, liquid water has been studied with many different techniques. I mean, we have X-ray spectroscopy looking at K edges, and so on. You have neutron experiments. This adds another technique to try to understand liquid water, but I don't think one can claim that just because we can study the timescales of ionization, we will have all the answers. I think it will be like a puzzle. You have to take into account many different techniques. It's a very complicated problem, and I have colleagues in Stockholm that have been working for decades on trying to understand liquid water. Combination of theoretical calculations and experiments. And you have these super cold phases of water that is very difficult to access experimentally, and so it's a huge topic.
Thank you.
Dear colleagues, some more questions?
I have one question. Is there any particular reason that this year Laurea have the denomination for their techniques and there is no any theoretician? You mentioned that there is some complicated calculations. So any particular reason, or maybe next year?
Yes, if I understand your question correctly, you wonder, should one have included theorists in this year's prize? But of course, this was discussed, but we considered that this year it was mainly an experimental prize. There has been, theoretical pictures of how you can produce these attosecond pulses, but primarily this was an experimental prize, and this also reflects in the citation where we emphasize for experimental methods in the beginning of the citation. So
thank you.
But I can expand on this a little bit just by saying that when we award a theoretical prize, there has to be an experimental verification of the theory. You cannot award a theory that has no experimental verification.
What would you say would be the implications for quantum theory in terms of the time energy uncertainty? Because now we have an attosecond pulse and we can take way less time to observe the state.
So your question is, what would be the consequences for the time energy relation? I guess you're referring to this version of Heisenberg uncertainty relation. Well, I don't see any. Of course, I mean the shorter pulses you have, the broader energy you address, and I think this will have consequences in attosecond chemistry, definitely. Yeah.
Thank you.
More questions? No questions.
Okay.
Okay, so if there are...
Maybe just one more question. What if we, in the water, in the gas state and the liquid state, what if we isolated the atoms so they would feel no influence from the other particles in the medium? Would the result be the same?
If I understand correctly, I mean, you wonder if there are other molecules in the water.
No? Not quite. I mean, if we would take a single atom of water in a state corresponding to a liquid state, and then repeated the experiment, would the outcome be the same?
I mean, in the experiment I showed you, you have at the same time both liquid and gas phase. So, yeah.
Okay, dear colleagues, no questions. Let's send Professor Larssona again for a very interesting lecture and interesting discussions. And now we have a coffee break.
Dear colleagues, dear friends, let's continue our session. My name is Professor and academician Mykola Kartel. The President Zagorodny Anatoly Glebovich passed me the right to continue our session. So I am with very big pleasure to introduce the next speakers, Professor Erika Aurella from the Royal Institute of Technology. He will deliver a lecture of black holes. It's very nice astrophysics thematics. You're welcome, Professor Aurella.
Take it again. Thank you, Professor Kartel, for the introduction. Dear colleagues, dear students and teachers for School 145. It is a great pleasure and honor to be here to give this lecture to students. I realized also already yesterday, let's say, but now also that there are senior colleagues and specialists in the audience, and I'm happy to say that I'm also going to give a technical talk on the same topic at the Bogolyubov Institute tomorrow about a paper which is on archive, the electronic preprint archive, since this morning. So today, let me start a little bit on my personal journey. I was also once upon a time a young boy or man who wanted to go into science, and I wanted to go into fundamental science, fundamental physics. And when I started doing that, I realized it's often very complicated and abstract, and therefore I changed fields and became a statistical physicist. And I worked most of my life in statistical physics in different applications to biophysics. Earlier it was on turbulence and on nonlinear physics. And very lately, thanks to a colleague who raised a question, I came back to this question of fundamental physics and black holes. But I come with the perspective of somebody who is, after all, mainly interested or come from the background of statistical physics. And I will try to present to you a problem, and I will try to present it to you in a very simple way. So the opposite way as it was when I was a young scientist. So everything will be very non-technical, almost everything. The things that are technical, I'm sure that the students from School 145 have already heard in popular science lectures. You probably know about it, or at least you've heard about it, and you'll see it here, and you can find the references very easily. But the basic argument I'm going to make is a very simple one, and I hope I will succeed in doing this. So that's why I call it the mystery of black hole entropy, and I will try to convince you that it is a mystery, and that the most senior people working in this field still today consider it a mystery. And with this, let me start. Black holes, one has to say these days that black holes are not the only topics that you learn about in a course on theoretical physics and gravitational physics, as it was in my time when I was a student. These are real objects in the universe that have been observed And here you see a rendering of one of the black holes that can be found in the center of one of the large galaxies. It's an amazing technical feat that, of course, what you see is the rendering of the gas that falls into the black hole. So the black hole itself is invisible, but you see the very hot gas, or you see a visualization of the measurement data that pertain to the very hot gas flowing into the black hole. And this can be photographed from Earth, which I think it's a technical marvel. And of course, as you already know, I'm sure you all know, the gravitational waves, which was typically an exercise in the course of gravitational physics after Weinberg's book when I was a graduate student. They have now been observed, and it's one of the Nobel Prizes. So we know that there are black hole collisions, and these black hole collisions, gravitational waves are generated and which spread all throughout the universe. So these are real objects in the universe, and since they're real objects in the universe, you can state the very basic question, do they also obey to the laws of quantum mechanics or not? And then that already raises the topic of the talk, which is that now almost half a century ago, one of the most influential physicists in the last century, Stephen Hawking, who did not get the Nobel Prize because his predictions were not verified during his lifetime, I think one can say safely, to the representative of the Nobel Committee in audience. He was a theorist. And as you probably all know, the students, you know, he had a both tragic and extremely unusual life. He was diagnosed with an unusual wasting disease, muscle and muscle nerve wasting disease when he was quite young. And he spent most of his time in a wheelchair, and for a long time towards the end of his life, he could hardly move anything, but he still managed to be productive until the very end. And he successfully retired from his professorship. He kept his professorship until retirement and then passed away a few years after that, outliving the projections of his doctors when he was, you know, young by more or less half a century. But half a century ago, he produced this theory, this prediction, which I hope now I will make the right choice with the laser pointer. Yeah. So he predicted something that one of his collaborators, and I think it's safe to say teachers, Oscar Penrose, has illustrated in this diagram. A black hole is born at some point in time by collapsing matter. And when this black hole is born first, the amount of matter which is inside the event horizon, from which nothing can escape classically, is quite small, but eventually all the collapsing matter is absorbed by the black hole. And here you can see the long, long life of the black hole. In the middle is something which nobody really knows what it is, but which is here pointed to as singularity. And these two lines, which you see here on the left and on the right of the wiggly line, these are representations of the horizon of the black hole. Something afterwards that falls into the black hole, like in the previous picture on this previous slide, will never leave. But eventually, this black hole emits radiation called Hawking radiation, at first very slowly, then faster and faster, and eventually at some time, the black hole in this picture disappears. That's why Hawking's first paper indeed is called Black Hole Explosions. It's published in Nature. It's more or less the same as content as the next paper published a year later, which has many more details. Classics of modern physics. Now, Hawking radiation is thermal at the temperature which is given in terms of Planck mass, speed of light, Boltzmann's constant, the mass of the black hole, and here comes the Planck mass again. So it's inversely proportional to the mass. And that's why in the beginning, when the black hole has formed and has swallowed all the mass of everything that fell into the black hole, the mass is larger, and then it radiates, and when it radiates, it loses mass, and when it loses mass, the temperature becomes higher. And so there is therefore an acceleration in the process of mass loss, and the effective equation, which is also written down by Hawking, is that the mass loss per unit time is still the Planck mass here, which is dimensionally mass, the Planck time, which is dimensionally time. So dm dt has dimension mass over time, and this ratio here has also dimension mass over time. And it turns out that it comes to the mass of the black hole over the black hole mass inverse squared. And so this inverse squared behavior that you see here by the Penrose's arrows being a bit sparse in the beginning and then become more and more dense as time goes by. There's also a prefactor which you come from the Stefan Boltzmann law and so on, which is less important for this discussion. So I thought that, you know, since there are students in the audience, we should give an aside about Planck units. Maybe you can all raise your hand. How many of you have heard of Planck units? Of the students. The students, you have not heard of Planck. So that is one of the complications that starts when you want to study fundamental physics. Suddenly the textbooks and the papers talk about Planck units, and you don't know about Planck units. You know about meters and seconds and kilograms. And then you wonder, why on earth would anybody be interested in expressing everything in terms of Planck length, which is 10 to the minus 35 meters, and Planck time, which is 10 to minus 44 seconds. And to give you an idea on how small 10 to minus 44 is, we had in the previous talk a Nobel Prize about attosecond, which is 10 to minus 80 second. And if you square 10 to minus 18, you will end up at 10 to minus 36. This is as an exponent the same as the Planck length, but then you have to divide the Planck length by the speed of light, and then you get back to 10 to minus 44. So 10 to minus 44 is much, much, much smaller compared to the attosecond. Then the attosecond is smaller to 1 second or to your heartbeat. So this is really a ridiculously small time, and this is a ridiculously small length. And together with them comes a mass, which is not at all ridiculous. It is actually 20 micrograms. You can probably feel it in your hand if you are very sensitive. If you would have an iron ball of 1 Planck mass, it's on the limit of what you can sense as a person. It's the scale of a grain of sand. So it's an object of elementary of everyday life. It's only if you consider it as a mass of an elementary particle, if that's what it has to be, then of course it's enormous. But as an object of elementary life, life is completely normal. So you have one object, one scale of elementary life, and then 2 scales which are ridiculous. Now, how come that the scale of elementary life mass divided by a ridiculously small time scale will give a ridiculously long time scale for the evaporation of the black hole? That's because there is the mass of the black hole over the Planck mass. And if you have an astrophysical squared, third actually, if the whole lifetime. So if you take this ratio of an astrophysical mass to a mass over everyday scale, you will have a very, very long time. Okay? So, and one advantage, actually, one of the first big advantages is that if you want to remember numbers in black hole physics, everything is much simpler in Planck units. So you only, for the radius of the black hole of the Schwarzschild type, you only have to remember the number 2, because of course the Planck length is dimensional length, and then you have the ratio mass of the black hole divided by Planck mass. So you have to remember one number. And the Hawking, same, you only have to remember the number 1 over 8 pi, because this is the Planck mass times c squared is the energy. You divide energy by Boltzmann's constant, you have temperature, and then you have the ratio here. So in black hole physics, it actually simplifies. Everything is dimensional numbers given by the Planck units, and then a few constants, which is all we need to remember. So from temperature, you can go to entropy. And since this is an elite school, 145, I suppose you already had courses in thermodynamics. Maybe you are great masters of thermodynamics already. Maybe you can raise your hand if you had, the students, I mean. If you had a course in thermodynamics, yes, indeed you had. Very great. So then you will either know or remember or recall that temperature is the partial derivative of entropy with respect to energy. So that's the formula. 1 over kBT is the partial derivative of the entropy versus energy. And the energy of the black hole is the mass of the black hole, that times c squared, of course. So if you insert now the temperature computed by Hawking, and you do a really simple integration, remember Hawking's temperature was inversely proportional to mass. So if I take the inverse temperature, I get proportional to mass. And if I integrate a linear function, I will get a quadratic function. And here's the function. So there is an entropy according to this formula, which is for a spherically symmetric black hole, the Schwarz uncharged black hole, non-rotating, the Schwarzschild black hole, which is 4 pi, which is the 8 pi changed into 4 pi, and then the mass of the black hole over Planck mass squared. So in fact, this kind of entropy for black hole was proposed before Hawking by another great physicist, Jacob Bekenstein, in 1972. So that's actually now more than 50 years ago. And therefore, when you call it BH, SBH, entropy BH, this means both black hole and Bekenstein-Hawking entropy. And then you observe, if you remember, this is actually a super extensive quantity. It scales faster than linearly with the mass of the object. While if you have entropy in condensed matter, which is, I guess, what we have seen, or maybe in gas theory, entropy is an extensive quantity, which scales linear to matter. So this already tells you that this entropy, if there is such an entropy, is a very different entropy than the entropies that you've already seen and that you're familiar with. So here's a slide a little bit for the specialist. Maybe for some of the students, if you have read some, popular science books, maybe you like to, just to see some backtrack that it's consistent with everything you heard before. So in general, if you're not considering a Schwarzschild black hole, that means a black hole which rotates and which is charged. In general, the BH entropy is 1/4 of the area of the horizon in units of Planck area. Planck area is, of course, Planck length squared. And that's usually or very often illustrated by this kind of tiling of the horizon, like with bricks, with these extremely small area. Well, these black holes are surely almost neutral, because real black holes in the universe, because if not, they would attract the opposite charge and they would neutralize quite quickly. And they don't spin extremely fast. So it's a good approximation to take the special case. And it's also a great simplification to take the special case of the Schwarzschild black hole. And for the Schwarzschild black hole, you have this formula, which already was in the previous slide. And if you insert for the radius, the horizon of the Schwarzschild black hole is 2, which is the number you need to remember. And then the Planck length, and then the ratio. And if you insert this formula for the sphere, for the area of the sphere, you get this formula here, which is the one I quoted on the previous slide. So mass of the black hole divided by Planck mass squared with some prefactor. Okay, so what is entropy anyway? Now, since you had thermodynamics, I can allow myself this luxury to discuss one of my favorite topics as a statistical physicist. Next year, in 2024, will be the 200th anniversary of the treatise of Sadi Carnot, Théorie de la chaleur, theory of heat, which is usually considered the starting point of thermodynamics as a distinctive and major field of physics. The concept of entropy was introduced by Clausius in the 1860s as heat in units of temperature. And heat, that is energy that cannot be used fully as work, as was the focus of Carnot's work. And the limitations are known as Carnot limits. This, I think, you must have all had in your courses on thermodynamics at some point. Now, from the modern point of view, there is an important branch of thermodynamics developed partly actually in Ukraine, although I'm not sure if this person, I would like to ask this to the specialist afterwards, I'm not sure if he's active in Ukraine and if he's alive, but anyway, the first papers of this was written by a collaboration with between the Ukrainian scientists and the scientists from outside Ukraine, but it's been developing mostly in the West, in Japan and in Europe and in the United States in the last 25 years. And that is the thermodynamics of not so large systems, which are used as which we call stochastic thermodynamics. And in this field of thermodynamics called stochastic thermodynamics, these old concepts of heat and entropy have been reconsidered because we needed them in a new domain. And so from this modern point of view, we would say that Claus's definition, the original one, is obviously of entropy production. That means change of entropy, because when you read it, it is the infinitesimal heat. The entropy change is the infinitesimal heat in units of the temperature at that moment in the process. And heat is also energy exchange, which is an energy change between a system and an uncontrolled environment. So the original definition of entropy is not of an absolute state quantity, but of an increment of a state quantity, or an increment, a change of something. But as you surely know, this has also been a little bit later by Boltzmann. He postulated that entropy is the logarithm of the number of accessible state to a system. And this is the way of the formula, the way it's written on Boltzmann's tombstone, except he uses W and not N for the number of accessible states for the phase space volume that the system can reach. And this formula with this way is a special case for the equal probable states for the Shannon entropy, which is this formula here, the sum of the possible values of the system, possible states of the system, the probability of finding the system in state I, and the logarithm of this probability. Because if you insert that all the probabilities are the same and all equal to 1 over n, then you find the log n, this number here, is the same as you get from the sum. Because you have n, big N terms in the sum. Each of the terms is 1 over n, so n cancels a 1 over n, and you have logarithm of 1 over n. And minus in front, logarithm 1 over n means logarithm 1 over n. So this formula is morally the same as this formula, is Shannon entropy, which has a large number of applications, a wide area of applications outside physics in the science known as information theory. So in all electrical engineering and computer science, it's a very important concept. If you come back to quantum domain, you can say that Shannon entropy is for the classical fields, what von Neumann entropy are for quantum states. So in quantum, you write it like this, where rho is a density matrix. And if you insert the special case that rho is a diagonal matrix, which is a classical probability distribution, then this formula is the same as this formula. Right? So because the sum of the probabilities have to be 1, and if you have a diagonal matrix and you know that the density matrix, the trace is 1, then you see that this formula is the same as this formula. So now we have seen two different views of entropy. One, which is the thermodynamic, the original one, and the later, which is the statistical mechanics, which is the one that goes back to Boltzmann. And the discussion of the relationship between these two types of entropy has a long history. I would say it has been the major fundamental topic of thermodynamics and statistical physics all since Boltzmann's time, with many contributions from many people. And here I highlight a contribution from a colleague of ours from Stockholm, Göran Lindblad. He's famous in quantum science for the inventor of the Lindblad equation. At least the experts in the audience will know this. Maybe some of the students have also heard this in quantum technology. In his long career, he wrote one single book, and this is the book called Non-Equilibrium Entropy and Irreversibility, which it happened to fall on me to write a perspective on the modern meaning of this book for a memorial volume, which we published just this year. He passed away last year. We published the memorial volume this year. So here's one person who spent a good deal of his scientific life to try to make the connection between the thermodynamic entropy in the Clausius original term and the information theoretical entropy, which you can assign to Boltzmann, Shannon, and von Neumann. And why is it a problem to relate the two? It's because in classical physics and also in quantum physics for isolated systems, the information theoretical entropy doesn't change in the evolution of a closed system. That means a system that does not interact with the environment. While the thermodynamic entropy is supposed to reach a maximum subject to the constraints that you put outside. So here's something which changes, and here's something which doesn't change. And I will skip the long discussion. This is one entry in many discussions. There is a general consensus, at least in classical statistical mechanics, how you square the two. But let's say, for the sake of the argument, if you have a thermodynamic entropy and you want to call it entropy, there should also be a statistical mechanic or information theoretical entropy. So there should be a phase space volume n. And here we come to the basic mystery. You can get all these numbers by Googling. It's not a problem. So the entropy of the star of the size of the sun, which of course is a function, a computable function of the gases that, which I never compute myself. I take it that the astrophysicists know how to do this. There is a layering of the star of the density from the surface to the core. There's an equation of state of the plasma inside the star. And from this equation of state, you can compute, or the astrophysicists believe that they can compute with good accuracy, the entropy of the star. And the entropy of the star of the size of the sun is, in units of Joule per Kelvin, is 10 to the 35. If you have a bigger star, you have a bigger entropy. Generally speaking, you have a smaller star, you have less entropy. Now, it's the if you have a black hole of a solar mass, so actually this is not what would happen in astrophysics. You need a bigger star for it to form a black hole normally, but to have the simpler estimate, you can then take the BH entropy of the black hole with the same mass and imagine that this one was actually formed by the gravitational collapse of the star. And then you already know that this, well, there can be some corrections because maybe density is different in different parts and so on, but basically this is an extensive quantity. The first one should more or less scale linearly with the mass of the star, while this one is a super extensive quantity. It scales quadratically with the mass of the black hole. And the number is 10 to the 54 joules per Kelvin for a star, or for a former star which has become a black hole. So there is a difference of 10 to the 19 of entropy. And now the question is, if now entropy is the logarithm of the available phase space volume, which phase space volume can increase by a factor 10 to the 19? Actually, that's a mistake. It should be 10 to the 10 to the 9. No, it should be e to the 10 to the 19. Sorry about this. I should have corrected this. So this is not 10 to the 19. It should be e to the 10 to the 19. That's an enormous increase of the available amount of states to the universe by a collapse which has moved all the mass into the black hole where it cannot get out. And actually, you can also read in the more technical astrophysical, here's a technical reference, but I think it's now 13, 14 years old, but I think it's still very interesting. And here's a very careful estimate of the entropy of different objects in the universe, published in Astrophysical Journal in 2010. This includes all galaxies, gases, includes dark matter, it includes nebula, dust of different kinds and so on, and it makes, a table. This has so much entropy, this has so much entropy, this has so much entropy, and it also has the entropy of primordial black holes, if such exist. That means very small black holes that were formed by the Big Bang, and astrophysical black holes. And those that we have observed in black hole collision have masses of tens of solar masses, and those that one observes in the center of galaxies have masses of millions of solar masses. And it turns out that more than 99.9999999% of the entropy in the universe today is actually black hole entropy, which is very strange. It means that out of the possible things, out of everything that you have in the universe, at least more than everything except one part in a million is hidden away inside black holes. And this is the mystery. And I give you a quote to remember, which is a wonderful quote, which one of the earliest texts available that you can find. It's from the ancient Egypt, actually found in the pyramid of an otherwise not very famous pharaoh. And it goes, "Open are the double doors of the horizon, unlocked are its doors." And you should understand this as saying a horizon, of course, opens things so that they can fall in and disappear. But if statistical mechanics in the Boltzmann sense still holds for whatever is inside the black hole, some other doors inside the black hole must be opened and give access to the universe to these new degrees of freedom that before were frozen out. Maybe if you are interested in arts, you know that there is a modern opera which opens by these words, but I will not tell you which one it is. But if you know, then you know. If you don't know, then you don't know. And I'm not sure I'm doing on time, but this is a possible first moment to stop. I can also go on.
Go on. We have time.
Sorry?
We have.
You have time? Yeah, okay. So, when you arrive at such a question, then you wonder, okay, is this question of the existence of the phase-space volume inside black hole, is this a right question? Is it the correct question? Especially if you come from the outside, this is the kind of question you have to ask yourself. And what could the black hole entropy or Bekenstein-Hawking entropy actually be? The literature on this, not really phrased this way, but the literature around Hawking, there is Hawking information paradox, there is Hawking radiation, and there is a black hole. The literature there is really around it enormous. But I think it's a fair, what I will arrive at here is a fair conclusion. And I will do it by following one of the last published texts by Bekenstein, namely the review that he wrote for this online encyclopedia called the Scholarpedia, which is like Wikipedia, but you have somebody who actually signed off that they wrote it. So this is Bekenstein, one of Bekenstein's very last published texts, which is his own encyclopedia entry about Bekenstein-Hawking entropy, written perhaps a little bit before, but made public in 2008. There's, of course, many reviews that I could quote about this. We quote many of them, but not of course, all of them in the papers that we wrote, and the one that's on archive today, and the ones that we have published before on this topic. I will not, that's for the specialists, just to say. This is one good summary of the possibilities. And he gives, that means he, in this case, Bekenstein, gives 7 possible explanations of the BH entropy, which I will go through to you. So, and I will give them in the same numbering as he gives in the Scholarpedia, but I will not do it in the same order. So there is the first part of 3 of them, which in Bekenstein's list is number 4, number 6, and number 7. That's explanations that somehow depend on new physics. That means physics which is not standard quantum mechanics, plus the kind of gravitational theory which you learn in a course on classical gravitation and relativity theory, then combined in the science about quantum fields propagating in a curved background of space-time. That is what I would say. Everything going beyond this is new physics. And there is one explanation which is due to Wald. Also, something like this was proposed by Penrose, which says that black hole entropy is a conserved quantity connected with coordinate invariance of the gravitational action. I am not sufficiently much of a gravitational person to really understand this definition, but this is definitely of the class of beyond quantum field theory in curved spacetime. There is the next one, which is that the black hole entropy counts the number of states or excitations of a fundamental string. There were a lot of excitements maybe 10, 15 years ago, where some extreme cases of black hole, these are the extremal black holes, these are not these ones, black holes, where you could count the number of degrees of freedom of those strings and then imply that they would also correspond to the Bekenstein-Hawking entropy in that limit. But that's also, that demands then that you believe in string theory, or that you know that you can work with string theory, which is beyond quantum fields in curved space-time. And then there's also saying that it's equivalent to the thermal entropy of the radiation residing on the boundary of the space-time containing the black hole. This is in the class of methods which assign something special, some special. The horizon is not only an invisible boundary where if you pass through it, you don't feel anything in the spaceship, but you can then not turn back. That is the picture which we probably all know from either popular science or from some first course of gravitation. This is in the class of theories proposing that there actually happens something other but then there has to be something non-local which happens to space-time around the horizon of the black hole. So these are three possible explanations, but which all demand new physics, so something else. And here three more, which focus on the horizon. One of them says that black hole entropy is the entropy entanglement between degrees of freedom inside and outside the horizon. This has been quite popular, but this of course implies the question, why is there no such entropy for any closed surface? You can think of dividing up, let's say, the solar system in what's inside the orbit of the Earth and outside the orbit of the Earth. Why don't we have an enormous entropy also for these two parts of space-time? Why is then the horizon special? There is another one which counts the number of horizon gravitational states, and there's a thermal entropy of the gas of quanta constituting the thermal atmosphere of the black hole. I have a feeling I've seen this before. But here's the main one. So there's only one of the explanations, which happens to be the first one, which I would say, which is on the level of the question which I raised. Black hole entropy counts the number of internal states of matter and gravity of the black hole. If you believe that the black hole entropy is an entropy in the sense of Boltzmann, this must be the answer. But then you read Bekenstein's explanation, which is quite general level and refers to two papers, one by two Russian scientists, Frolov and Novikov in 1993, another one also by a Russian scientist in some sense. He says, man, it's a person both Mats Larsson and I know well, and in the last years he started to say that his real name is not Mukhanov but Mukhan, because he's Tatar and he's not at all in favor of Russian politics in many ways. Anyway, so and Jacob Bekenstein, who was a very humble man, didn't say that actually the first estimate in this direction is by Bekenstein himself in 1973. So there are three estimates in 73, 93, and 2003. And all the three of them have in common that they don't talk at all about what are the internal states of the black hole. They just talk about estimating the number of different ways in which the black hole could form by estimating how many quantum states of ordinary matter could have fallen into the black hole and given rise to the black hole. Then, assuming that this number is conserved, you say that the black hole must encode which of the specific, in its internal dynamics, whatever it is, it should encode which of the specific initial states of matter actually fell into the black hole. And then by counting of how many of those states there actually could have been, you get an estimate on how many internal states there must be in the black hole to encode for all of them. But it doesn't say how they do and which it does. These estimates are not exactly the same, but they're all on the same ideology and all more or less arrive at similar value. They arrive at a similar value, but they don't proceed in details which are entirely the same. So here's the second part where I can stop. This is the most important problem in fundamental physics. And I think I hope to have convinced you that the masters, at least one of the main masters, Jakob Bekenstein, and you can also read many other masters and you can convince yourself it's the same, they don't know the answer. So students in school 145, may you find out. This is a problem for the future for you. And may you all live and prosper. Thank you.
Thank you. Thank you very much, Professor Aurellla, for your very interesting lecture. And we have some time for the discussion. And if anybody have question, please, you may.
Yeah.
You're welcome.
Thank you. I have a question about the Horizon event.
Maybe you can speak up. Can you speak up a little bit, please? I don't really hear you.
Sorry, I have a question about the entropy. You said that the way black hole is get bigger, the bigger than entropy, yes?
Yes.
Can it be explained with the increases of the horizon, even horizon? I guess it's called like that, this part of the black hole. And maybe it's because the increasing of this event horizon. I don't know, horizon event.
Okay, let's see if I can reformulate it. Yes, there is a general formulation which I skipped here, which says that the black hole entropy is the area of the black hole, and of course that's dimensionally length squared. So you have to have make it undimensional in some way. And you make it undimensional by dividing by the Planck length squared. So this, and then there's a numerical factor, which in this case is 1/4. Okay, now, so 1/4 area over the length squared. And you can find many papers concentrating on this and using this form of the entropy as an argument that it really is the horizon of the black hole, which is really important. I try to be agnostic here and not to say anything for or against this. That is the horizon that's really important. And why? Because what you perhaps know from courses in gravitation is that the way a black hole is usually pictured is like an invisible boundary. So you fall towards a black hole and you don't feel anything in the rocket yourself. You pass through the horizon, you don't see it. This is what the classical textbook would say. Then eventually, when you pass through deep into the black hole, you hit the singularity, and then you feel it, and then you're dead. So this is what the way, but if you assume a physical nature and a physical origin of the entropy to the horizon, and you give that amount of stress to the horizon and to formulate the horizon, then you also should propose some new physics at the horizon. So that's a kind of explanation which I did not focus on today, but there is a large literature following this remain. Now, for most astrophysical black holes, they are almost surely electrically neutral and very good approximation. And they rotate, but they don't rotate extremely fast. They are very far from these extremal black holes. So if they are neutral and non-rotating, the formulas of black hole physics simplify, and you get this Schwarzschild black hole, which is spherically symmetric. And if you insert then the radius of the Schwarzschild black hole, which is this formula which appeared on several slides, you get this other formula which I concentrated on today, which says that the black hole, the entropy is the mass of the black hole squared divided by the Planck mass. So what I was talking about is, if you like, a special case of a more general formula, but which allows to bring out the difference in the dependence on mass. Mass squared is a super extensive quantity, and it is in many ways extremely strange. If you have a super extensive entropy, you will have a negative, you make, the compressibility is sort of the opposite that you have in ordinary matter. That's why you lose matter, you radiate matter, but actually the black hole heats up. And if you have a piece of burning coal, for instance, when it radiates energy, then of course the coal will lose energy and the temperature will go down. Okay, so these things are all connected in that the entropy of the black hole is it's of a different kind than ordinary entropy. I hope I answered all the points that you raised. Maybe not, then you have to ask again.
Thank you very much. Pretty much understood what you were saying. It's hard, but thank you. And I have another question about the metrics. You said about Schwarzschild metric. I know that it's for non-rotating black holes, and I guess that some harder part is about the rotating, like Kerr metric, yes? Or Kerr
Yeah, I
Newton
didn't
metric.
mention the Kerr black hole, but of course it's called Kerr black hole when it rotates, yeah.
And it's the most, I guess, cool way to explain Einstein's equations, yes? Like way more cooler than another one, non-rotating. Because I saw in the media, popular media, that it's usually called like that. And maybe it's like determined in science another way. I guess that's a weird question, sorry. I was interested in that while I was reading Gravity by Misner, Wheeler, and Thorne. So that's why I'm so active. But maybe I should, I don't know, sorry.
No, maybe I don't get your question here in the way that it's different, but I can say that this famous textbook by Wheeler and Thorne, of course, it's so old that even I had it as a student, yeah. So I still have it in my office. It's a great book, but it contains a little bit too much, I think. Yeah, so I prefer actually Weinberg's book, which is more short and to the point. But it's also a very old book. Both those books are about 50 years old. Huh? Yeah.
So we got the harder explanation in the Kerr-Newman equations, like for rotating black hole that's way more complicated to explain entropy.
Yeah, for the students. So Schwarzschild was a German astronomer who was mainly an observational astronomer, I think, who in almost, I think, immediately after Einstein had published this theory, the general theory of relativity, Schwarzschild found this fantastic solution of a spherically symmetric solution which has a singularity and which has then the horizon. Not all the properties of the solution was clear from the beginning, but the mathematical form was clear already then in 1916. And it has many advantages. One of them is that you can write down the formulas. I did not write down here the solution for the metric of the Schwarzschild black hole, but you can do that quite easily. You only have to remember one really simple polynomial, and it goes in the numerator for one term in the metric and the denominator in another term in the metric. That's all you have to remember. And then, of course, you have to remember the factor 2, because that's the radius of the Schwarzschild black hole. Now, if a black hole rotates, it will be compressed, so it's no longer spherically symmetric. It's compressed at the poles. And then you can add also, if it has an electric field, then there is some more to this. And there is another formula for the horizon, which is more complicated. There's a formula for the metric, which is more complicated. And yeah, it's more difficult to present in a lecture like this, especially if I have nothing really to say about the Kerr black hole that is any different than what I can say about the Schwarzschild black hole. Therefore, I prefer to talk about the Schwarzschild black hole. But of course, Kerr is the general case, and Schwarzschild is a special case of Kerr. That's how it is. Yeah. Or Kerr-Newman, if you prefer. Yeah.
Thank you.
Any more questions? Please. Welcome.
So the question is that there are a lot of scenarios of the end of the life on the Earth, and I would like to ask how is it likely that the end of the life on the Earth will end by the capturing on the Earth by the black hole?
Let's see, can I repeat the question? I think your question is, how likely is it that the Earth will end by colliding with a black hole?
Yeah.
Well, you know, we can estimate backwards, and for sure this has not happened in the solar system for a long time. We have so we have not observed it in historical time. That means since at least the time of the pharaohs, anything like this. I think the ancient Egyptians and Chinese would have noticed in the annals if you had it. So the probability cannot be that high. Then if you extrapolate backwards, all the theories of the solar system more or less say that it's been about the same way for a bit more than 4 billion years. Then, of course, you have to go to specialists in space science to actually have these numbers, but I think that's believable. So we have not been close. We have not had any close encounter with the black hole for the last 5 billion years. That's pretty short. Now, so the chances of our hitting a black hole lurking somewhere in the universe is most likely not very large. Of course, there is the problem of extrapolating from the past to the future. This is, you know, but we have no reason to believe that suddenly black holes multiply in the universe. Likely this will not happen. Now, 2 more things we can say about this. One is that we will probably not have much of a warning. If there is a dark black hole sitting somewhere in the universe, in the galaxy, and our solar system is in a collision orbit towards this black hole, I suppose we would first see it that some of the comets and the outer members of the solar system would start to behave strangely. And then we would have maybe some days or weeks of pre-advancement until also the Earth starts to behave strangely and, you know, rotate around the black. So it's not the question that we will, you know, wake up, go to bed one evening and we wake up next morning and we are also inside the black hole. Doesn't go that fast. But I think it will, Mats can correct me if I'm wrong, I think it would go pretty fast if we'd have a direct collision of the black hole. One thing that could be the case, that's something that I discussed with my more, you know, abstractly oriented colleagues in Stockholm, is a primordial black hole, which at least in some theories is the explanation of dark matter. Doesn't have to be, but it could be. If so, there should be a lot of primordial black holes, which are of mass something like 10 to the 13, 10 to the 14 kilos today, or not less, because then they would have evaporated, perhaps more. And they would be extremely small. So they would have much less than 1 attometer in radius. So we would, perhaps there are some primordial black holes trapped inside the Earth. This is not impossible because they're so small that their cross-section with the ordinary matter inside Earth is almost 0, and they could probably go around in the nucleus of the Earth for a very long time and hardly gain any mass. So they would, in some sense, eat, if there is one there or many, they could eat up the Earth from the inside, but it probably goes very, very slowly. And the same thing with the sun, of course. Yeah. Yeah.
Okay, thank you. And one more question is that, like, if we get the Planck time, so this is very small number, like ridiculously small,
yeah.
Like and it's even smaller than the other second. Then what is the way of measuring the Planck time?
There's no way at all to measure anything like the Planck length and the Planck time. They are much, much below present measurement technology. Let's say, I think the smallest one is for the gravitational waves. I believe they measure 10 to the minus 20 something meters. Mats will know better. 21. I hope this is not filmed. I mean, this is on Zoom, so the whole world will know if I make a mistake. But it was a ridiculously small distance, but this distance is then compared to the Planck length is more than 10 orders of magnitude smaller. So the distance in length between the smallest that has been observed today and the Planck length is larger than the ratio between 1 meter and the size of the atom. It's a larger discrepancy, but it's not quite the ratio between 1 second and 1 attosecond. So it's something in between.
Thank you.
More question, please.
Excuse me, please, if my question will be incorrect or even stupid. I'm not a scientist, but a journalist with a master's degree in political science. Could the black holes in our universe accumulate all the matter and turn our universe to an empty space without any other objects?
Could is not a word in the vocabulary of physics, because in physics we believe that things are determined. So that is not what comes out. Actually, there are two reasons that the answer is no. So one reason is that even if you have no Hawking radiation, that means that the black hole, if they swallow everything, that comes into them, the universe is expanding, and many parts of the universe are outside the black hole, and the universe is expanding actually at an increasing pace. So the black holes that we have today will go further and further apart, and the parts which is in between, which will, at least it will take an exponentially a very, very long time until they eventually run into a black hole. And trying to extrapolate now, I think that actually there will be quite a lot of part of the universe which doesn't actually never reach a black hole. But then the answer is no for a second reason too, which is that according to Hawking, this of course has never been observed, and the prospects of direct observation of Hawking radiation is for the moment very uncertain, but it would change an enormous amount to physics if there was no Hawking radiation. According to Hawking radiation, even black holes eventually radiate. That means that they evaporate and disappear. So the way we say as physicists now envision the world to end, if you like, or to be, is that we now are in a phase of an increasing expansion of the universe, and that will accelerate. All the stars will eventually die out, all the galaxies will die out, everything in the universe will be pulled apart faster and faster. And the black holes will also, after some long time, release their contact in the form of light. First, very, very low energy light, so radio waves and even longer wavelengths, and then eventually in the form of X-rays, the last one possibilities. And after this, all the word is single particles of light and matter, which are alone in the universe, which is becoming more and more and more and more sparse. This is what science points to today, but it will happen in a long time, and it's nothing that we need to worry about here on Earth. We have more problems, even on Earth as a body, that will happen long, long before this.
Thank you. And one more question, please. Where do the black holes lead? The Irish tales tell us there is, for example, a pot full of gold on the other side of rainbow. And what can we find on the other side on the end of black holes if they have the other side?
Okay, so the first answer is we don't know. Nobody knows. If it may be nothing. The other answer is, maybe you're specifically referring to the theory that black holes are actually always connected to a hole, to some other universe. Maybe this is so, maybe this is not so. That depends on, or to another place in the universe. We don't know. But it is a mathematical possibility that the black hole is a tunnel, is a way to go to somewhere else, especially a rotating black hole, as we heard here before. So, but this is a specialized topic. If these channels are stable and if you can traverse them or not is another. It's a specialized topic which somehow is outside this discussion I had today. But we don't know. Maybe nothing.
Thank you for your answers, for the report, and for coming to Ukraine. Thank you.
Yeah.
Any more questions? You have. Our girls are more active than boys. This lecture. Вопросы в чате? We have in Zoom.
A question in Zoom? Okay. Mhm.
How many black holes are in the universe? Stellar mass, middle mass, inactive galaxy, nuclear, etc.
I think this is a question from an expert, perhaps at least, and I'm not an expert. I will present tomorrow a technical talk at the Bogolyubov Institute, which will also be Zoom. And then if I cannot answer the questions of this type correctly, then for sure some of the experts at the Bogolyubov Institute can answer. As far as I know, in the black hole in the universe, it is believed that almost every galaxy, perhaps not quite every, but almost every galaxy has a large black hole in the middle. And that has been observed in many galaxies, though not in all. The amount of black holes which are not these large ones in the middle of the galaxy, I think it's an open research question. It was not expected that one would find these collisions of black holes with masses of tens of solar masses when they were found in gravitational waves. It was up to then, this is not so long ago, it was believed that there are very few such black holes in the universe, at least at that epoch. And that turned out to be not the case. There has now been found many such collisions. So I think this is not known how many there are. There is some upper limits, of course, but I think one is very far from them. That's the answer, the best answer I can give to the first question. Then the second question, the possibility of the Earth to be collided by a black hole. This is a question for the experts in dark matter. It depends on which expert in dark matter you talk to. Some of them say that this scenario that dark matter is black holes is completely ruled out and they don't believe it. And some of them, they say that it actually is a possibility and it's getting more traction because some of the other dark matter candidates have problems. This goes for the previous favorites like such WIMPs and so on. So it is a contender. Then it depends on how many of those black holes which were formed in the early universe, which are called primordial, they are. And if there are too few, then the chances of anyone hitting Earth is of course very small. But you know, just to say, it's a theoretical possibility that maybe there were some, enough, and one of them could perhaps be trapped in Earth. Of course, this is speculation. And just to end, it was in the reply of one of the earlier questions. I hope this is okay. Yeah. So I will give a more technical talk tomorrow about my own work at the Bogolyubov Institute. So then I welcome all technical questions.
Thank you. Professor Laurel, maybe last question from me.
Okay.
I am not specialist in astrophysics, and so my question is a dilettante on this. What is it? Dark hole. You may give us the short definition. What is it? What is the type of cosmic?
A black hole is a solution of Einstein's equation for gravity. A black hole is a solution of Einstein's theory of gravitation, which has the property that it has a horizon. A horizon is a surface, a surface in space from when you pass through that surface and you are on the inside, even light cannot go out. Of course, a material object has to fall down and even light cannot go out.
That is a special situation, interaction or overheading between matter and energy, or not? How to explain the existence of soul type system?
Yeah, you can say it's an effect of something like this was speculated already in Newtonian gravity a very long before Einstein. So you have, of course, the larger the body, the stronger is the gravitational field and the more difficult it is to get out from the body. That's why if you try to get out from the Earth, you can do it by a rocket, which we can build. If you would do it from an asteroid or even from the moon, it would be much easier. But if you would try to get out from the neighborhood of a much more a larger planet like Jupiter, then it's more difficult. So the larger the body, the more difficult it is to get away from the body. This was known already since the time of Newton. Now, the general relativity of Einstein adds, if you like, makes the gravitation, when it's stronger, there's an enhanced strength of the gravitational potential, the gravitational interaction, when it's quite strong. This is called, to borrow a phrase from the book which was mentioned here before, it's called a pit in the potential. So this means that you have a rocket, eventually any rocket that you can have would be able to leave the neighborhood of the black hole. Then you can go one step further and to say, okay, now let's suppose I am in the rocket. Can I send out a light signal and report where I am? Yes, when you fall towards the black hole, for a long time, you can report this light signal and it will come to you more and more redshifted, because it will be redshifted when it climbs out the gravitational well. And the horizon is the surface in space where the redshift is infinite, so that you will never get out. The light will never get out. And when you're inside the black hole, then even light signals, which are, if you are a rocket falling through the horizon into the black hole and you send out a beacon of light, then part of that light will go towards the center and it will go faster than you and hit the center faster. And part of it will go away from you and try to get out of the black hole. But that just means it will not fall as fast as you do towards the center. It will also hit the center, but later.
Very short definition.
Well, the first definition was it's a solution of Einstein equation which has horizon. Yeah.
Thank you very much. I think we may end our discussion. Yes, enough. Let's thank once more Professor Aurellla. Thank you. And so, thank you very much. And so we have a small addition, a small video will be presented by Professor Larsson. Few minutes, very short.
Yes, we will end with a video recorded by a person who attended School 145. This will be a simple lecture in classical mechanics in a short video, and I will start this video now. It was recorded some 20 years ago in something called the Hercules Games here in Kiev.
Victoria, maybe we help some self. Help yourself, please. Ось що робить з людьми 145-та школа. Sorry.
Ребят, смотрите, это был 2000 год. Вот, я тогда занималась пауэрлифтингом. Ну, я уже выступала в сборной Украины 8 лет. Вот, и соревнования были в Киеве. Назывались они богатырские разваги. Вот, Strongman Competition. И они пригласили меня как бы для шоу. Вот, и сказали, что будет колесо 340 килограмм, Я к нему никогда не пробовала даже. Я просто занималась в зале, я тренер, и до сих пор 30 лет я уже тренирую ребят таких, как вы, и постарше. Вот. И когда мне сказали, что будет колесо 340 килограмм сегодня, а завтра я должна его поднимать. То есть я просто села и подумала, как я это могу сделать. То есть на то время моя тяга, вы знаете, что такое тяга, когда штанга стоит на полу, ты должен ее поднять. У меня была 190 килограмм, а колесо 340. Вот. И, в принципе, как бы мы можем рассчитать 340 пополам, ты поднимаешь его снизу, потом как-то нужно подсесть и перевернуть. В общем-то, если бы посмотрели, как мужчины это переворачивают, они в физмат-школе не учились. Техники у них, не было здесь. Просто я уже спустя 20 лет посмотрела, я это сделала идеально с первого раза, с 340 килограмм. Вот. В принципе, мы хотели закончить таким, что не только в науке, то есть можно сказать так, что на протяжении всех лет, после окончания школы я закончила университет, но, к сожалению, не пошла в физику, хотя университет я закончила геофизику, Шевченко университет. Вот, но потом я поняла, что я слишком сильна, закончила, получается, университет физического воспитания и спорта в Украине, в Киеве, и также высшую спортивную школу в Стокгольме. Вот, то есть сейчас я очень профессиональный тренер. Если у вас будут вопросы, как стать сильнее, это ко мне. У Игоря есть мои координаты сейчас, у вас есть тренажерный уголок внизу, возле школы. Вот, и я надеюсь, мы будем на связи.
Вопрос. Виктория, вы используете знания о черных дырах в своей деятельности? Черные дыры. The program of our session is over. In conclusion, I wish everyone new creative achievement, peace and security, and see you again. Next meeting will be. Thank you everybody for the attention. Thank you our Professor Larsson, Professor Aurello, and Victoria, Dr. Victoria, for very interesting communication. Thank you all.